Okay. With that. First of all, thank you for the invitation. It's a pleasure to be for the first time in India. So, well, I'm going to give this series of 3 lectures, and my intention is to introduce you on this topic on which I was working in the last years with Leo Margolis mostly, and with other collaborators, also with Andrea. And at the beginning of his lecture, Eric mentioned a book that we wrote recently, a few years ago. Maybe it's not that recently, 3 years ago. Anyway, but what I'm talking is what is not in the book. Okay? So when we started, that could have been in the book, but then the book became too big, and then we decided that there was not a space for this part. Well, let's see. Let's see. Maybe somebody can write that book, that other book. But okay, my intention is to be really elementary. Okay, so please, I'm going to try to do all the proofs. Some of the proofs that I intended to do, Sugandha did this morning in the tutorial, but maybe I can remind you again. And parts of the proofs uses some problems who are in this handout. So I will distribute this later, or maybe I can start distributing it. So you please start passing. Okay, so take some here and then you pass it. Okay, and there are everything that I'm going to say is in the lecture notes that is in the web page of the conference. So you can also see that there. But please don't open this now, because I want you to take notes. Okay, okay. So you don't need the laptops. Okay, you can close them, and so I will try to lecture us in a bachelor or master class. Okay, so try to not to go fast and not to go to. So I want to be. Luckily, somebody. I'm borrowing some glasses of somebody else because mine broke, and with that, without them, I will have a problem. Well, let's start with fixing some notation that during these days, okay, some people have using different notation for the same thing, which is the augmentation ideal. Okay, no, the augmentation map. So you start with a group algebra, and you have this map, which is the augmentation map. And there are wonderful people that like to call them omega or W. Probably they consider this is a wonderful map. And some wonderful people or some excellent people that call them epsilon. Okay, I don't know why W or omega are epsilon. And that's why I decided to increase the confusion and call it AUG. Okay? So, and this is the map, which simply sum the coefficients of the group ring element. Okay? And this notation have 2 descendants. Okay? One is coming from a normal subgroup, and one is coming from any subset of the group. Okay? This one coming from the normal subgroup, already Eric mentioned, is when you go modulo n, okay, and just you simply sum, well, go to the classes, okay? And the book, we use this wonderful notation, and we use it also GN to denote it, okay? And this other map, what it does is summing the coefficients in the set X, okay? So I like to call this relative augmentation, relative modulo n, augmentation modulo n, and these are usually called, in some special cases, partial augmentation, because you sum of the coefficients. Okay, so just I wanted to fix this notation. Of course, now I prefer to use this to be consistent with this, and this has generated this notation. Okay, so in this way, maybe it's worth to have the two notation because the descendants are called differently. Okay, because they are different, of course. Well, in the talk by Eric, he has talked a lot of subgroup of finite index. So big subgroups in the integral group ring, but I want to go to the other way. So the topic in my talks are finite subgroups, or even more restrictive, torsion units. Okay? Just to build an intuition, let's start with a number theoretical result. Okay? Which this morning, Eric mentioned Dirichlet theorem, which is about units in number fields. Actually, in the group, in the ring of integers of a number field. You start with a number field. Now you take the ring of integers, and the units, this is the result, is here you have a finite group, actually a finite cyclic group, and this is a pre-abelian group. And of course, if I don't say anything else, this is nothing because there is no theorem, because this is finitely generated, and as every finitely generated abelian group is finite times torsion free of a given rank, of rank. For me, this is not important because what I'm talking now of the torsion elements, and of course the torsion elements form this cyclic group. Okay, so in this special case, the torsion element form a cyclic group. Okay, and in a particular case which is similar to the one that we are considering, because now we are interested in the case of we want to understand units in set G for G a finite group. What is this? Basically, you are adjoining to the integers some torsion units, a finite group. Okay, so what is in number theory something which is similar to this? This is essentially a cyclotomic extension of the rationals. Well, actually, the ring of integers is the adjoining to the integers a root of unit. And a particular case of this Dirichlet theorem tells you that, of course, the torsion units form a cyclic group, but actually the torsion units of this guy basically is formed by the units that you use to define it. Okay, so it's essentially, well, the group generated by the root of unity if n is odd, and the group generated by, well, 2n. Okay, this is my notation for a primitive nth root of unity. Complex. complex primitive nth root torsion. Okay, in case, no, this is the other way. This is if 2 divides n, and if 2 does not divide n, this is the so basically, you use some torsion element to define your group, and the torsion units are basically given. By the way, in this second case, in this case, theta n is the same as theta 2n. So you can say that the only. So, and well, we wanted to understand problem is how are the torsion units of set G, or more generally, how are the finite subgroups. Okay, already Eric mentioned, and this helped to increase the confusion, that the units can have augmentation 1 or -1. And the confusion was how you denote. Well, this is the notation that we all use for units, and is formed by plus minus the units of augmentation 1. Okay, so these are units with augmentation 1. And well, in the book we denote it this way, but I was influenced by the Germans in the latest year, and so lately I denote it this way. Victory, no? That V comes from victory. Anyway, so you only, so we can restrict to this type of group. Whatever you say for the victory units, for the units of augmentation 1, you already know for all the units. Okay, and of course there are some obvious torsion units, which are the trivial units, the ones coming from the book, from the group. Okay? Okay, and the Berman Higman theorem that have appeared here two times, and this is going to be the third time, is it was proved independently by Berman Higman. Says that if you have a unit, it's a torsion unit, torsion unit. If 1 is in the support, or the coefficient of 1 is non-zero, then U is plus minus 1. Okay? What the result? I think that I should not prove it because you proved it 1 hour ago or 2 hours ago. So it's okay, it's in the notes. And as a consequence of this, the torsion central units are trivial. So belongs to plus minus the group. Actually are formed by the plus minus the center of the group. And the proof is very simple. Even if you prove it this morning, I will do it again. If U is a torsion central unit of G, okay, of course, it's non-zero, so something is in the support. You take an element in the support of U and take U G inverse. Of course, when you multiply two torsion elements, the product might not be torsion. But if they commute, the product is torsion. Because one of them is central, they commute. So this is a torsion element But the coefficient of 1 here is the coefficient of 1 of G in U, which is non-zero. So 1 is in the support of V, and because of the Berman Higman theorem, this is a torsion unit with 1 in the support, so it's plus minus 1. But this is UG inverse, and so U is plus minus G. It's a trivial unit. Okay? So in particular, if G is abelian, because my group is always finite, okay? I won't say it constantly, but okay. If G is abelian, then the torsion units are all trivial. Okay? And this has a very strong consequence on probably the most important problem for group rings, which is the isomorphism problem. Isomorphism problem asks whether if the group rings are isomorphic implies that the groups are isomorphic. Okay? And another consequence of the Berman Higman theorem, rather than of the last corollary, is that the isomorphism problem has a positive solution for abelian groups. The proof is now a triviality. Well, Eric more or less explained how it goes, the proof. So if you have an isomorphism, first you prove that you can modify the isomorphism so that it preserves augmentation. Okay? So the isomorphism restricts to an isomorphism between the unit groups, but if it preserves the augmentation, it gives you an isomorphism from the units of augmentation 1. So in case these guys are isomorphic, not only the group of units are isomorphic, but also the torsion, the units, the group of units of augmentation 1 are also isomorphic, and therefore the torsion part here is isomorphic to the torsion part here. But the torsion part here is G. The torsion part here is. Okay, so G, which is the torsion part of this guy, is isomorphic to the torsion part of the other side, which is J. Okay, so understanding finite groups or torsion units has consequences on other problems, like, for example, the isomorphism problem. Finite abelian groups. Well, not necessarily. You don't have to assume that, because if one is abelian, one algebra is, one of the rings is commutative, then the other is commutative, and this implies that the other group is abelian. Yeah. Correct, correct. Yes. When I say that way, it's for both groups. Okay. So there are cases where you might have one group has some property, of course. Yeah. Well, that depends. Okay, that depends on how you formulate it. It can be for a class of group that if both are the same class, then they have to be isomorphic. Or if one is in the class, then the other is in the class, and then they have to. Well, it's isomorphic, then it's in the class. Okay, so, and there's another kind of problem is if certain class of groups has to be close and the isomorphism of the group ring, for example. Sorry, what? This one? This one? No, no. This morning, no. This is a domain and a group ring of a finite group is a domain if and only if the group is trivial. Impossible. Okay, the group rings of finite groups are never domain, except for the trivial group. Okay? So you need several of these somehow to construct the group ring, more or less. In the tutorial of Uganda this morning, more or less you can. Anyway. But there are more consequences of the Berman Higman theorem. It is really a very strong result. One of them, already Eric mentioned, says that every finite subgroup of units of augmentation 1 is linearly independent over the rationals, which is the same as saying over the integer. Okay? Well, so I promised to prove everything. This is what I'm doing. So take H, a finite subgroup of the units of augmentation 1. So on, let's enumerate the elements here, H1, Hk, say. Okay. Let's suppose that we have a linear combination which is 0. Okay? Linear independent over the rational is the same as over the integer. So we may assume that the coefficients are integers. I want to prove that all the coefficients are 0. Okay. Well, only one of these guys is 1. Okay? And all of them are torsion. But I can multiply by any of them. So I'm going to prove that C1 is 0, and then the same proof works for the other. And for that, I multiply here by H1 inverse. Okay. So these are, again, the group elements. Of course, the product is 0, and the sum is 0. And now calculate the augmentation. Of course, the augmentation of 0 is 0. This is the sum of the augmentations of this guy. I mean, the augmentation is a linear map. But these are all torsion elements. Okay? But the only one which has 1 in the support is this one, because these are non-trivial. And the Berman Higman theorem that the non-trivial elements, torsion elements, have 0 in the support. Okay, it has 0 as I mean, 1 is not in the support. So the coefficient of 1, no, this is not the, so the coefficient of 1, Okay, what is the coefficient of 1? Here, of course, is C1, but here is 0 everywhere. And the coefficient of 1 here is 0. So C1 is 0. And the same proof works for the others. So all the coefficients are 0. Okay? Okay. So the torsion subgroups cannot be as big as you desire. Because how big can be a linear independent set in a finite dimensional space as big as the dimension. So the subgroups has order at most the order of the group, the finite subgroups. So this gives us restrictions on the torsion subgroups, and in particular on the torsion units, on the order of the torsion units. Okay? But we have something more. Okay? And this is the order of every finite subgroup of units of augmentation 1 divides the order of the group. Not only at most the order of the group, but it's actually a divisor. Yeah, please. Right? Correct. But there are torsion units. Okay? So we can apply the Berman Higman theorem to them, because there are torsion units. Okay? So if they are not 1 or minus 1, the 1 is not in the support. So the coefficient of 1 is 0. And this is what I'm calculating here, the coefficient of 1 in this sum, which is the sum of the coefficients of 1 everywhere. But because these guys are torsion elements, which are of augmentation 1, because they belong to here, and different from 1, so the coefficient of 1 is 0. So when I calculate the coefficient of 1 here, I get 0, and in all of this one. And here the coefficient of 1 is C1, of course. This is why this is C1, and of course the coefficient of 1 here is also. Okay, so they don't have to be in the group, but this is the important thing of the Berman Higman theorem. Why it's powerful. Well, to prove this, first I need to prove a lemma. Which says that if K is a field, well, field extension of Q. I could say that it's a field of characteristic 0. And E is an idempotent, okay, different from 0 and 1. Then the coefficient of 1 in E is rational number, rational, and in the interval 0, 1. Not 0, sorry. 0, 1, yeah, correct. This for any field doesn't matter. So the coefficient of 1 has to be rational and in the interval. Okay, so let's prove the lemma first, and then we prove the proposition. Well, we take the regular representation. Regular representation. So we use G, for example, as a basis, and we are representing as matrices in that basis multiplication by the elements. Okay? Representation, and it has a certain character. Say high is the character afforded by rho. Okay? So high is a linear map, and to know how is high, we need to understand how is high on the group elements. But when you calculate row of a group element, what you obtain is a permutation matrix where you put 1 in the places, in some places, and zeros everywhere else. Okay? So this is a permutation matrix. Actually, you put 1 in x, y if gx is y. Okay? But of course, if g is not 1, in the diagonal, you only put zeros. There's no 1 in the diagonal. Okay? So I for an element different from 1 is 0. But of course, if G is 1, this is the identity, and so G is the identity map, the trace is the cardinality of the group. Okay? And because this is a linear map, okay, when I apply my linear map to the idempotent, what I obtain is exactly the coefficient of 1 in E times the cardinality of the group. Because so I is linear combination is, say, well, this coefficient says C1, 1 plus other coefficients. When I apply high here, high in G, you get 0, and here you obtain exactly the cardinality. C1 times the cardinality of the group. Okay? But the representation of an idempotent is another idempotent. Okay? And every matrix, every idempotent matrix can be diagonalized. And the diagonal form of row of E is exactly a matrix like that. Okay? So the trace of row E, which is exactly high of E, is exactly the number of 1 here, which is the rank of row of E. The rank of this matrix. So it's an integer, a positive integer, which is, it is at most the cardinality of the group. But because it is neither 0 nor 1, and the regular representation is injective, the rank is neither 0 nor the cardinality of the group. So this is an integer between 1 and the cardinality of the group minus 1. Okay? Okay, then this is that integer say k, and so C1 is k divided by the cardinality, but this k is an integer between this and that, so it's a rational number, which is more than 0 and less than 1. Okay? So the idempotents are also special. Okay, so no, at least the coefficient of 1 in the idempotent is not an arbitrary object. And now I'm proving the proposition. In all the Blackboard, and I have been told that I should not use the top part. Okay. Well, and now we are proving the proposition. AH, a finite subgroup of units of augmentation 1. Okay, and we take H hat, which is the 1 divided by the cardinality of H, sum the elements of A. And this is an idempotent. Okay? This is an idempotent. Okay. So if I calculate the coefficient of 1 in this idempotent, is a rational number between 0 and 1. Okay? But if I apply the high, remember the character afforded by the regular representation, the regular character, to E, okay, what I obtain is exactly the coefficient. So say the coefficient of this is sum of E, G, G. So we obtain E1 times the cardinality of the group. Okay? And yeah, of course. And this is between, this is a rational number. Okay? Okay. What else? But the coefficient of one of each of these elements, these are elements of torsion elements in our integral group ring. So by the Berman Higman theorem, the coefficient of 1 in all of them is 0 except for the coefficient, I mean, for when h is 1. Okay? Where, so the coefficient of 1 here is 1 over the cardinality of h. Okay, because when h is 1, the coefficient of 1 is 1 times 1 over h, and the others is 0. Okay. No. Wait a minute. And now I did something wrong here. I'm sorry. Yeah, correct. This is the coefficient of, high of 1 is the cardinality of G. Okay, this is high of E is exactly the cardinality of G divided by, because high on all the group elements except for 1 is 1, and in 1 is exactly the cardinality of the group. Okay, but this was an integer. Okay, so the order of the group divided, the subgroup divided, so this is an integer. So the order of h divided the order of the group. So this tells us that there is more rigidity on the torsion groups that at the first you may expect. Okay, so you cannot find, so the group, the original group, is telling you a lot about the subgroups. Okay? Okay. Well, in particular, the order of every torsion element of augmentation, every torsion unit for augmentation 1 divides the order of the group. Okay? Well, the fact that the torsion units in the abelian case are only the elements of the group, plus all this information suggests that, okay, maybe you only need the group to produce all the torsion elements somehow. In the abelian case, it's true. Of course, in the non-abelian case, you cannot expect that, because you can start with a group element, which is a torsion element, and conjugate. Then you have other torsion elements. You cannot expect that when you conjugate, G is not going to be stabilized by conjugation. So you might say, okay, maybe this is the only way to produce torsion elements. You start with a group element, start conjugating, okay, and then you have all of them. Maybe. Okay, and this apparently this was Zassenhaus at a certain moment. So okay, maybe this is true. Maybe this is true. Maybe, but actually it's not true. Actually it's not true, and already Higman knew it. And in this problem number 11, I think, you can prove that. Okay, so this will, so my proposal is that you try the problems. The first problems are very simple, are very easy. Okay, for example, one of them is proving that a torsion, an idempotent matrix can be diagonalized, or a torsion matrix can be diagonalized, and some others. Okay, but in problem 10, there is a way to prove that in the smallest non-abelian group, finite group, so the symmetric group on 3 letters, there is one torsion unit which is not conjugate. Well, it's not conjugate. When you say conjugate, you have to say where you conjugate. Of course, the natural thing is in the same group where you are working, of course. Okay, so in that problem, you can show that in the group of units of your integral group ring, there are torsion elements which are not conjugate to the elements of the group, but they are conjugate over the rational group algebra. So every element in this particular group, every torsion unit is conjugate. Every torsion unit of augmentation 1 is conjugate on the rational group algebra to a group element. I like to think of that as a kind of a diagonalization problem. Think on a matrix with integral coefficients. Maybe it can be diagonalized. Not over the integers, most likely. Most likely you need to conjugate with a matrix. And if you can do it, if it can be diagonalized and it has rational coefficient, in particular if you have integral coefficients, you need a matrix. You can do it with a matrix with rational entries. Okay? But maybe not one whose inverse is already, I mean, the rational you can multiply by something so that it has integral coefficient, but the inverse may not have integral coefficient. Maybe it's not invertible over the integer. Okay? Okay, and so this produces what, I mean, Zassenhaus conjecture that every torsion unit is conjugate in the rational group algebra of an element in the group. Okay, so this has been disproved recently, and Leo Margolis contributes, is one of the authors of a counterexample to this. So now I'm not going to call them conjecture anymore, by problem, because it still is a problem if for a particular group this statement holds. So the Zassenhaus problem for me, the first Zassenhaus problem, well, actually not clear if he posed the 3 of them, but at least this one he poses is whether every torsion element of this G is conjugate in the rational group algebra to an element of G. Well, there were other first conjecture and in the end problems because all of them has negative solution. So it's the same question, but not instead of for torsion elements, for finite groups. It's rationally conjugate to a subgroup of G. Okay, this is the third one. And the second one, so I change the order because I write something, is for the subgroups which has the same cardinality as the group. Conjugate to G. Okay, the third one, or the second one, is important because a positive solution gives you a positive solution for the isomorphism problem. Because if it's rational conjugate, they are isomorphic, of course. Okay? Of course, because we know that the isomorphism problem has a negative solution since 1997. Okay, when Hertweg came up with a countersample, of course, C2, the last problem there, so the number 2, has a negative solution. But we knew that before because for other results. Okay, so now we know that the 3 problems have negative solutions. So there are groups for which they fail. But now the question is when they are true, well, somehow the Zassenhaus conjecture was a nice solution to the question, the original question, how are the finite subgroups, how are the torsion elements? So now we know that this conjecture is false, so it's not the correct answer. So now we need a new possible answer that we don't know. Okay? There are other questions which are related. Some of them are still open. For example, if the Zassenhaus conjecture, the first one, were true, if every torsion element is conjugate to some element in the group, the order of the torsion elements are orders of elements in the group. The set of the orders of the torsion elements is called the spectrum of the group. Okay? The spectrum is you take all the torsion elements and calculate the orders, and this is a set of integers. The question is whether the spectrum, this is the spectrum problem. Is the spectrum of the units of augmentation 1 equal to the spectrum of the group? This would be another nice solution. Well, they are not conjugate, but at least the cyclic groups are isomorphic. Because a cyclic group is isomorphic to another one if it has the same cardinality. Okay? So this is open. It's true for solvable groups. This is a result of Martin Hertweg, but it's open in general. So, and there is a weaker version, which is whether, well, what is called the prime graph of these 2 groups are the same. What is the prime graph of a group? Arbitrary group, abelian or not. So you put vertices just for primes B, which are the order of a group of an element in the group. One vertex for every prime that you can encounter one element. And now the edges, there is between P and Q, if one edge, of course, is an undirected, not if G has an element of order P times Q. Okay? Of course, this is something about part of the spectrum. Okay? About the prime elements and the elements of order prime and elements product of 2 prime, of order product of 2 prime. Okay, so the question is now, the prime graph question. Galileo like to call it PQ, because for P and Q, like it that way. Anyway. Say that whether the prime graph of these two groups, of this set G, and prime graph of G are the same. This is also open. Okay, of course. It's true for solvable because the spectrum, positive answer for the spectrum problem is a positive answer for the prime graph question, obviously. Okay. There is a reduction, a group. I mean, for a group satisfy this property if and only if every almost simple epimorphic image satisfies the condition. So some people, these two guys there and some others, are proving for many simple and almost simple groups using the classification. You might in the end prove it that, but there's still a lot of work. And time is over, so I should stop. Thank you very much.